Good morning, everyone. I hope that you're all well and keeping safe. What we're going to do is we're just going to go through this set task that I gave you. I'm only going to do about half of it because I've only got a 5-minute recording time here. So it was for waves and radiation, which is this booklet that I sent you here. And so I'm just going to go through the first bit of it. The first thing that we're going to look at is wave properties. So the idea about waves is that, as it says there, waves are everywhere. You guys are going to have to be very familiar with that. Out at sea, it's nautical. We've got examples here of an earthquake, which is basically a seismic wave causing huge destruction in Nepal, which is this one here. And then we've got the sound wave here travelling from the vibrations of a tuner fork into your ear. And the key point here is that there's energy being carried. An example of that would be, say, a bat or something sending out sound waves, and then the prey of the bat here, the sound waves reflect back, and the bat can go and get its dinner. And out at sea, of course, you're going to see these waves, and hopefully none as big as this. So the key point is that waves are basically energy that's rippling through space. That's the key point. So there's two types of waves. First one is called longitudinal wave. A longitudinal wave, if the direction is along here, the wave vibrates to and fro along that direction. It's like a wave in a spring or something like that. Whereas a transverse wave, and a good example of that, by the way, would be a sound wave. A sound wave is longitudinal. The other one is transverse waves. The transverse waves, they vibrate at right angles to the direction that the wave is travelling in. So if the wave is going this way and you were sitting on that wave, you would be moving up and down like that. So basically radial waves are the best examples of this, but also waves and strings. The book says Mexican waves, don't listen to that. And also it says water waves. Water waves are actually not transverse waves. So the summary which you should have is all waves transfer energy. Transverse waves vibrate at right angles to the direction of travel. Examples of transverse waves include light, waves and string, and microwaves. Longitudinal waves vibrate to and fro along the direction of travel. And an example of longitudinal waves are sound waves. So now we get on to wavelength. Wavelength is just the distance between two peaks or two troughs, or from that bit to that bit. That these bits are one wavelength apart. They're in phase, we say, with one another. To measure wavelength, you use a symbol called lambda, and it's actually the Greek letter L. Now the amplitude is just the maximum height of the wave. All right, it's measured from the 0 point there. So the amplitude is that height there. Now, in some waves, the amplitude is literally the height. In other waves, the amplitude might be the volts. It could be decibels for sound waves. It could be whatever the energy is for the wave. So I've got a little practice problem here. You have to work out the number of waves from the number of waves, the wavelength of the waves, and the amplitude of the waves. So here we've got two waves in 10 meters. So the amplitude is 3 meters, which is that, and the wavelength is going to be 2. It's going to be 10 over 2. In this next one, we have 3 waves, 1, 2, 3, and 15 meters. So the amplitude is going to be 15 over 3, which is 5. I have no idea what the amplitude is because it doesn't say. This one, the amplitude is 1.5. It's not 3 because this is from trough to crest here. The crest is the peak and the trough is the bottom part. So remember, the amplitude is just the distance from the centre out to the crest, so it's 1.5. There's 2 wavelengths in 10 centimetres, so the wavelength is going to be 5. And then with this one, we've got 24 metres here. There's 1, 2, 3, 4 waves. So the wavelength is 6 meters and the amplitude is going to be half of 10, which is 5. The frequency is how many waves there are per second. So it's just the number of waves divided by the time, n over t. You can change that about to get that the number of waves is frequency times time, or time is number of waves over frequency. And from that, you can get what the period is. The period is the time taken for one wave. So to get that, you just take 1 over the frequency. So an example, what is the period of a 10 Hertz wave? Remember, 10 Hertz means 10 waves per second. So the solution is that the period is 1 over f, which is 1/10, which is 0.1 of a Hertz. So my 5 minutes is nearly up on this, so I'll post the other one up pretty soon. Thank you very much for watching.